Good morning in Taiwan, and good evening in Florida, and I think good afternoon in Europe. Welcome to this webinar series on which is mini moon number 6. And for number 1 to 5, please go to our website and you can see the videos. We have now almost 30 lectures from distinguished scientists. And today we have Dr. Zhu Landsman from University of Central Florida. She's an expert on the moon. And she's a scientist, a project scientist at the project in Florida Space Institute. Maybe later on you will tell us a little bit about that also. And she's embarking on a very interesting and ambitious project, trying to to build a skyscraper, right, on the moon. And but firstly, I would say that Dr. Landsman, she got her bachelor degree from the University of Central Florida, and then later on she also went into the graduate program there. So received the PhD degree from the same university, and so she's a real, how we call it, Floridian.
Thank you so much for inviting me to this seminar series. I'm excited to be able to talk about some of the stuff that we're doing here at the University of Central Florida. It's good to everyone, and you can see my slides. So my background is in planetary science. My PhD was actually in observational astronomy, studying the surfaces of asteroids. And since then, I've become more of a general planetary regolith surface researcher, using observational and laboratory techniques. And what I've been working on most recently is a project to develop and characterize regolith simulants. So that's part of my work with the Exolith laboratory at the University of Central Florida. So that's what I will talk about today. So I wanted to start by telling you about the Exolith lab, where we make simulants. So this is part of the Center for Lunar and Asteroid Surface Science, or CLASS, which is a NASA Survey Virtual Institute. So it's funded by NASA, but it lives at the University of Central Florida. And our mission at the Exolith lab is to develop and produce simulants, analog regoliths, for the moon and Mars and asteroids as a service to the scientific community and to the exploration and engineering communities. So our simulants are sold at cost. So we're not a business, and we're not trying to make a profit off of this. We're just trying to sell them so that we can keep making more simulant and keep the lights on at the warehouse. I wanted to tell you a little bit about our simulant philosophy, and that is that we really begin with the mineralogy of the body that we're trying to simulate, because the mineralogy is going to drive a lot of the important properties of the simulant. So we begin with mineralogy, and then we identify the key properties of a regolith, and I'll talk more about that later. But it's important to figure out what are the properties that your simulant really needs to be simulating, so that you can say whether your simulant is good or not, how high its fidelity is. And it will allow you to grade the simulant against some reference material, whether that's samples, in the case of the moon, for example. For asteroids, we have samples in the form of meteorites, and soon, and now actually we have samples from various sample return missions. And of course, there's also remote sensing data. And in the case of Mars, there's in situ data collected by rovers. Let's see. So we do that. Another important part of our philosophy is documenting the development of our simulant, the production of our simulant, and being very open and about what our simulants do well, what they simulate well, and what they don't necessarily simulate well, because there are no perfect simulants. We're using material that comes from the Earth, and so it's not going to be exactly the same as the material we're trying to simulate we also don't have, the material we have is not space weathered, and I'll talk more about that. And we're in a 1G environment. So, we just want to be clear about what applications the simulant is good for and what it's maybe not as good for. And at the same time, we have this problem that we call constrained maximization. So we want to get the best fidelity that we can get while keeping our simulant cost effective. Some groups want to buy it in very large quantities for testing, I don't know, rover wheels or drills and things like that. So we don't want it to be very expensive, but we want it to be good. We also want it to be safe, and we want it to be useful. So those are the parameters that we're keeping in mind with our process. So I just wanted to tell you that this is a big team. I won't read you the names of every single person on the team. My role here in Exolith is on the science side. So I'm the chief scientist. So I lead a lot of the analysis of the simulants and development of simulants, and help people in the scientific community decide what simulant is going to be good for their application. The principal investigator of Exolith is Dr. Dan Britt, who I believe already gave a talk in this seminar series, so you might have heard from him already. But we have a good and diverse team of scientists and engineers. I also wanted to mention we have many undergraduate students who work on our team. They assist us with research, and they also work actually making the simulant, which is hard work. It's physically hard work, and it also requires a good bit of knowledge. So we're very lucky to have some very good, hardworking students. And outside of our team, we of course collaborate with many other researchers. Many of them are at UCF, experts in planetary science, but we also work with people in industry, NASA, and we have really a big team of collaborators through CLASS, which is again our NASA survey node. Okay, so what are some applications of simulants? How do people use simulants? Well, there are many ways. One big simulant application recently is studies for in situ resource utilization processes. So some examples of that are studies of water extraction, getting water from regolith, studies of additive manufacturing. So how do you build things? How do you build structures in space? Human housing, bricks, tools, things like that. Molten regolith electrolysis to extract metals from regolith is a big field recently, and that's a nice application for simulant. And of course, people use simulant to develop and test their spacecraft hardware, rover wheels, drills, things like that. Along these lines are dust mitigation studies. I'll touch on that a little bit more, but mitigating dust was a huge problem in the Apollo era, and it will be a big problem for the return of humans to the moon going forward. So figuring out how to keep the dust at bay is a tough problem and a good use for simulants. And then, of course, there are scientific studies using simulants across many disciplines. So the figure here is from a set of impact experiments using one of our asteroid simulants to study impacts in very weak, very porous asteroid material and get some more inputs for models. That's just one example, but there are people all across planetary science and astrobiology who use simulants for many, many studies. And then, of course, for education and outreach, it's really nice too, because it's a tangible thing that you can see and hold and look at, and you can look at the colors of the simulant and things like that. It's a really good tool for teaching about regolith. So this is just a very simplified description of our simulant development process. So how do we come up with a simulant? And it might be pretty much what you expect, but I'll go through it briefly anyway. And this is focused, this particular flowchart is focused on the moon and lunar simulants, but the same logic applies for any other kind of simulant. So, you know, first we would look at what we know about actual samples of the moon. Most of those were collected during the Apollo era, the ones that we have access to and the data we have. But of course, there's also remote sensing data that can be quite useful for areas of the moon that weren't directly sampled by humans. So we look at those samples, we learn about those samples, and then we find appropriate terrestrial analog rocks and minerals to stand in for the minerals that are in the lunar regolith. So we find those, we crush them to the appropriate particle size distribution. That particle size distribution is confined by or constrained by what we know about the moon or Mars or asteroids, but we can also customize that for different uses. We can make it coarser, we can make it finer. We then combine the crushed minerals into our final simulant. But of course, after that, there's more that we can do if it's called for. So we can, like I said, crush it or sieve it to change the particle sizes. We can add other materials like an agglutinate simulant, which can be really important for the lunar regolith. We could also add a minor mineral phase, or if we're talking about asteroid regolith, we could add organic materials or something like that. So we can do a lot of tweaking and customization just depending on what somebody needs. So here I want to describe how do we verify the minerals that we bring in. So if I go back for a second, we get these rocks to put in our simulant, but before we crush them up and make a huge batch, we want to make sure that the rocks we have are what we think they are and that they're pure. So we can do that in-house at the University of Central Florida. There's a materials characterization facility where we can get X-ray diffraction and X-ray fluorescence data for each mineral that we bring in. And the combination of those is a very powerful tool for assessing the composition of a mineral, because you can, so the X-ray diffraction will give you this characteristic spectrum that's really a fingerprint for the crystal structure of any particular mineral. The position of these peaks will tell you which mineral it is, and then combined with the X-ray fluorescence, which tells you about the bulk elemental composition, you can be pretty certain what your mineral is. And so we look for any evidence of any large amount of a contaminant phase. I will say that there usually are some amounts of contaminant phase, by which I mean, usually some kind of weathering product, because these rocks are coming from quarries on Earth, and they have been weathered, they've been exposed to water, and they've been exposed to air, and so they're not pristine minerals. There are going to be small amounts of alteration products. So we just try to make sure that those those contaminants are small in quantity, and this is the drawback of being able to make these materials in very large quantities. And we do make sure to publish the results of these analyses in an analysis report, the Exolith constituent analysis report, which is available on our website. And I think I have the website somewhere in these slides. But it's a living document. So as we, if we get new data for a mineral, we'll put it in there, just because we want, many people are curious about everything that goes into the simulant, of course. So we want to share any data that we have. Okay, so I thought next I would just describe our lunar simulants that we have. We do also have, again, Martian and asteroid simulants, but for the mini moon seminar series, of course, the lunar simulants are the most relevant. So so we have two main lunar simulants. One is a Highlands composition, and then one is a Mare composition, so representing the two main compositional units on the moon. And I would say the majority of people recently have been using the Highlands simulant, and I think that's really driven by NASA and the Artemis missions focusing on the lunar South Pole, which is Highlands Regolith. But of course, you know, a lot of the moon is also Mare material, so that's available. The Highlands simulant. So I should have put the reference here, but we base the composition of these simulants on Apollo samples that were collectively decided by the lunar science community to be representative Highlands samples and representative Mare samples, respectively. There was a lunar, now I can't remember the name of it. It's when I say the Lunar Sample Consortium, I think that's the name of the group. But if anybody wants to follow up with me later, you're welcome to. But there's a publication on representative samples. So we looked at the representative samples for the Highlands and then for the Mare, and took essentially an average mineralogy from there. So this is the breakdown of the ingredients, the recipe, you might say, for our Highlands simulant. It's mostly anorthosite, which is mostly the mineral plagioclase. We also add in a glass-rich basalt, and that serves two functions. So the basalt, you know, there's some basalt present in the lunar Highlands that has been transported from the Mare region. But the fact that the basalt is glass-rich allows this simulant to have some of the properties it simulates some of the properties of the glassy component of the lunar regolith. We are working on, and I will talk about that in this talk, we are working on an agglutinate simulant to do that a little bit better. But for somebody who wants just to buy a huge amount of this for their rover test bed or something, this does a pretty good job. And then there's smaller amounts of the iron titanium oxide ilmenite and olivine and pyroxene. So here's the bulk chemistry. So this is just, this bulk chemistry table is not something that we aim for. This is just what we get from the mineralogy, and it's reasonably close to lunar samples. And then here's a plot of the particle size distribution. So the bigger points here, the bigger darker points are the particle size distribution for the simulant, and then the curves in the background are the representative Apollo Highlands samples. So at least from the 100 micron size on down, it's a reasonable match. And here is the same data for the Mare simulant. So the mineralogy is different. I mean, it's the same minerals, but in different proportions. So if I go back, there's the Highlands, and then the Mare, it's quite different. So primarily pyroxene and basalt, some anorthosite, and olivine and ilmenite. And again, here's the particle size distribution for that, and pictures. So these are our main simulants. And again, this particle size distribution, this is kind of the standard, but we can alter it as needed. So I wanted to mention briefly, and I know Dr. Britt had probably discussed this in the seminar series as well, but I wanted to mention dust and dust hazards on the moon, because that drives one of our new simulants that we developed. So dust was a really big problem throughout the Apollo era, and will continue to be a problem for any really human or robotic missions on the lunar surface. So if you have humans, there's health concerns from your skin being irritated to silicosis of the lungs from inhaling the dust. But then there's also destruction or degradation of life support systems, spacesuits, airlocks, degradation to flight systems, any kind of mechanical systems, bearings, gears, seals, any kind of scientific instrumentation, sensitive telescopes. These are all going to be negatively affected by the dust. The lunar dust is very irregularly shaped. It's very abrasive, and it's very fine-grained and cohesive. And so that's a big problem to tackle with any discussion of surface operations on the moon. So we've had a lot of people who have reached out to us asking if we could come up with a simulant that is really just the very fine dust, so that they can study how their bearing or their seal or their coating for a material, how that responds to this very, very fine dust that's really the hardest to deal with, or their filters, how do their filters work with it that they're developing. And sieving the simulant to this very fine size is not, it's very impractical from a time standpoint. It takes a very long time to sieve the fine particles out because they're so cohesive, and we're in Florida and it's humid and things stick together. So rather than sieving, we've just decided to crush the simulant longer and make it very fine. So this is the particle size distribution for what we're calling LHS-1D, so our Highlands dust simulant. So the red star points here are the particle size distribution for the dust simulant. And this vertical line represents the 25 micron particle size. So nearly 100%, maybe about 98% of the material in the dust simulant is finer than 25 microns. And we have a comparable product for the Mare as well. It's a different, since it has a different proportion of the minerals, it takes a little bit of a different amount of time to crush it. So we're still narrowing in on that, but it's available soon. So that's that. And so I mentioned this, here's the other thing that we're working on, which is an agglutinate simulant. So agglutinates are these irregularly shaped, very interesting particles found in the lunar regolith that are, they're made of lunar regolith, but they're welded together in a porous, glassy matrix. And these particles are formed by space weathering processes, especially bombardment of micrometeorites. And the percentage of agglutinates in the lunar soil is a function of how mature that soil is. So the longer it's been weathered, the more agglutinates you'll have. So we're in the process of developing a simulated agglutinate, and we have our process down pretty well at this point. So what I've shown here on the bottom picture are some actual lunar agglutinates from an Apollo 11 Mare sample. And here on the upper right are some of the these welded glassy agglutinates that we're developing. They're made of the simulant, so the glass is made from the simulant materials. They're probably a little bit on the big side compared to lunar agglutinates, so we're figuring out how to crush them and maintain some of that morphology that's so important. But we're envisioning that this will be either a simulant component that somebody could choose to add. So, at any particular fraction that somebody wanted, we could add it to the simulant, or if they just wanted the agglutinates on their own, we could do that. This on the left here, this is an optical thin section image. This is in reflected light. So this is one of our agglutinates, or several of our agglutinates of Highlands composition. And the dark material here is the glassy matrix. And then you see there are some air bubbles in there, and then there are particles of this is mostly an orthosite from the lunar simulant. And just for reference, here's a picture of an Highlands agglutinate from an Apollo sample. So that is in the useful quantity shortly in the next, I would say, weeks to months. Okay, so the last topic I wanted to cover about simulants is how do you test them and evaluate them? You know, it's really important to assess which properties of the lunar regolith do you care about as when it comes to your simulants. What do you want them to simulate? And then measuring those properties in your simulants and establishing some kind of quantitative grade or figure of merit to compare your simulant to the actual lunar regolith in terms of these important properties. So the table I've shown here is from a lunar simulant workshop in 2005, where the scientific community met to discuss what are the important properties in a simulant. And I've highlighted the ones that are the top 10 that the group found. And so that's really what we're, for the most part, that's what we're focusing on. We have a number of measurements that are in progress right now, measurements of our simulant. So that includes the abrasiveness of our simulant, how its abrasivity, the angle of repose of the simulant, its compressive strength, of internal friction. We're also testing the flowability of the simulant. We're looking at particle shapes with SEM imaging. We're doing spectroscopy to learn a little bit more about the optical properties. Also looking at magnetic susceptibility and thermal conductivity. And I should mention that some of these quantities, you know, we don't necessarily have comparable data from the lunar regolith. So like the abrasion data that I'll tell you about, you know, we don't have this exact quantity for the lunar regolith, but in that case, these quantities can be, you know, this will represent the best guess that we have about what the lunar regolith is like. So these can be useful as inputs to models or as constraints in spacecraft development and things like that when you don't have any data for the moon in that particular topic. So I'm just going to highlight a few of these tests that we have some preliminary results for. But again, this is, you know, these are all still in progress. And our goal is to publish these in the scientific literature and on our website so that anybody who is curious about any of these properties of our simulants can find it. So we've been doing direct shear testing. So if you're not familiar with this test, and I wasn't until relatively recently, being an observational astronomer, this is over the last few years I've learned more about this. But the idea is that you have a shear box that has a top part and a bottom part, and you fill that box with simulant, and the top part is disconnected from the bottom so it can move across, and then you load a variable mass representing a known normal force, so some weight on top to induce a normal stress, and then you apply a shear force along and shear off that top portion of the box. And if you are to make a plot for each normal stress, so depending on how much weight you put on top, for each normal stress and each corresponding shear stress that you need to displace that box, if you plot that, you'll get a linear looking curve, and you can fit a line to that, and the slope will tell you the angle of internal friction of the simulant or the material, and the y-intercept will tell you the cohesion. And so we've done this for our lunar simulants and actually almost all of our simulants at this point. The value of cohesion in particular has been something that people have requested from us a lot, because it's, it's an important regolith property, and people want to know, does the cohesion of this simulant match the lunar regolith? So for both simulants, we get around 0.3 kilopascals. The Mare simulant is a little bit more cohesive, but this is reassuring because there's a range of cohesion values represented or reported for the lunar regolith, but they're generally in the range of anywhere between 0.1 and 0.7 kilopascals. So that's reassuring about that. I mentioned that we're also studying how abrasive the simulant is. We're doing this with a 3-body abrasion testing rig. This method was developed by Ryan Kobrick and collaborators, and so we work with him to get some of this done. The idea is that, so this is what the test rig looks like, and the idea is that you have this rubber wheel, and you load simulant against the wheel, and then below that there is some material, some standard test material, and the wheel is going to spin and force the test material against the surface that's going to be abraded, and at a known angular velocity and for a known amount of time. And then you study how much volume is worn away from that material that you've abraded. So the graph that I've shown here is, so the vertical axis is the wear volume of a standard aluminum. We chose aluminum because that's what many spacecraft are made of. So it's the most relevant. And then we look at what volume in cubic centimeters of the aluminum was worn away by different materials. So on the left here, these are kind of our standards. So alumina, powder, and silica sand, essentially. And then we've looked at a number of simulants. So the least abrasive are these two simulants here, which are Phobos simulants that the Exolith lab created. And these are more of like an asteroid composition with more clay material. So it's not surprising that they're less abrasive than, so for example, LHS1 and LMS1, these are our two lunar simulants. They're much more abrasive. They wear away more of the aluminum. This is an older generation Highland simulant. So it's interesting. We're not quite sure how to interpret the difference between the older lunar simulants and ours. So that's something we're thinking of. And then on the right here are two of our Martian simulants, which seem to be the most abrasive of all. So we have a little bit of work to do to think about why that is and what the implications are. But it's interesting. It's interesting data to have. And then the last analysis that I wanted to mention is spectroscopy, visible and near infrared reflectance spectroscopy. So this is exciting for me as an observer. I love seeing this kind of data. I've shown here the spectra of our two lunar simulants. It's not surprising that they look fairly similar because they're made of similar materials, just in different quantities. They look pretty characteristic of the spectra of the main minerals in there, olivine, pyroxene, and plagioclase. I think this sharp absorption feature that we see in LHS1, I think that is perhaps some kind of evidence of a weathering product, like an aqueous alteration product. So that's something I want to investigate a little bit more. But what I want to point out is that if you've seen a reflectance spectrum of the moon, you would say that these really don't look anything like the moon. The reflectance spectra of the moon tend to be very, very red in slope, so much higher reflectance at longer wavelengths. And the lunar spectra tend not to have very obvious absorption features. And the reason for that difference is space weathering. So the plot that I've shown at the bottom left here is a plot from the M-cube data on the Chandrayaan orbiter. And using the spatial resolution available, this was from Peters and Noble 2016. So this is looking at mature lunar soil and then moving toward a crater. with fresh soil. And you can see how the mature soil is very red and very, the features are very attenuated. And then as you move to the fresh, less weathered material, you see the red slope starts to decrease and the absorption features return. So this is a good point to mention that our simulant is not space weathered. You can, the primary driver of these spectral changes from space weathering is the production of nanophase iron, which happens over very long periods of time from the bombardment of energetic particles onto the lunar surface. And that is something you can do in a lab, but it's hard and expensive, and you can't do it with a large quantity of material. So, the mechanical properties of the simulant might be very close to the lunar surface. There are some optical and chemical changes that happen as a result of exposure to space that are difficult to replicate, to simulate, especially if you want to keep your simulant inexpensive. So this is just to point out, here is this kind of brown spectrum. Here is the spectrum of the Mars Global Simulant from Exolith. This was developed by Kevin Cannon, and this was from his paper on that simulant. And this simulant, so the pink and blue dots here are some spectrum of actual Martian soil. So the Martian simulant is a much better spectral match because it's not the same, there's an atmosphere, and so there's not the same weathering environment as there is on the moon. So it's bringing me toward the end of this talk. I just wanted to bring it back and mention that one of our goals and one of our purposes at Exolith Lab is to provide science support to anyone who is doing science with simulants and to make custom simulants. So we can customize simulant, whether that's particle sizes, adding certain materials that you might want, customizing the shape or configuration. We can make cobbles, pebbles, bricks, that kind of thing. And you can always reach out to us to get a simulant consultation if you want to use simulant in your science and you're just not sure if it's going to work, or if you're not sure which simulant to use or something like that. So, through those consultations, you have access to me, but also to Dr. Britt. Jared Longfox is a geophysicist and a geotechnical specialist with an engineering background. So he is available to consult on a lot of topics. But we also have access to this class team through NASA of experts on the moon and Mars and asteroids. So if you have a question about your simulant and we don't really know, if we can't answer that for you, then we can find somebody who can. So so we're here to help. And then yeah, that's all. Thank you so much. If you have questions, I'm happy to answer them. Thanks.
Yeah, thank you so much, Dr. Landsman. It's a very nice talk, introducing all the work you're working with the Exolith lab. First, I ask the audience whether anyone have questions. If you have questions, you could unmute yourself and then they ask the question to Dr. Landsman. Let me ask a couple myself because I'm quite interested. Actually, I have quite a few. In your last slide, you talked about using the regolith to make bricks. And how do you make bricks on the moon? Because there's no water.
Yeah. I mean, so if somebody wants a brick of simulant, we have a few ways we can do that. The main way that we've done that in the lab is using, we'll use a binder material. We've used sodium silicate, which is if you mix it with water and then add it to the simulant, it will bind the simulant particles together, but it doesn't significantly change the overall bulk chemistry. It just adds a little bit of silicon to the total bulk chemistry. So we'll do that for a purpose where it's appropriate. Like somebody might need, a big block of stuff for their project. If you're on the moon, that's a thing that we've been thinking about, is how do you do additive manufacturing to make bricks on the moon? There was a great paper that just came out. Now I can't remember the author's name, but there was a paper on additive manufacturing using different kinds of simulants, and it was really like a review paper. I'll see if I can find. I think it was in Acta Astronautica, if anybody wants to look there. But there are all kinds of ideas about using whether you could use the sun to melt things, whether you could, what processes you could use to weld simulant on the moon, what kind of binders you can use. So that's not something I've personally done a ton of research on, but I know that people are using simulant to study that.
Very good. Since you're expert on asteroids, so I dare to ask you this question. What's the difference between the physical properties of regolith on asteroids, on the moon, and on Mars?
Yeah. Oh, yeah. That's a good question. Yeah. I mean, the mineralogy is really different, especially when you're looking at asteroids compared to the moon or Mars. So the moon and Mars are, their surfaces are very thermally altered. Those bodies were molten and they differentiated, and so they have a crust and a mantle and a core. And so the regolith is made of crust material. It tends to be like on the moon and Mars. It's a lot of plagioclase and pyroxene, basalt, things like that. Asteroids are much more primitive. So most of them are from bodies that did not fully melt or differentiate. And some of them are from the colder parts of the solar system. So they have more clay minerals, a lot of organic, especially the carbonaceous asteroids, the C-type asteroids have a lot of organic material, potentially water and ice and things like that. So they're much less evolved.
Mm. So you're talking about the chemical compositions, right? Because
right. So as far as the regolith, it depends. I mean, asteroid regolith, the lunar regolith is very, very fine. Asteroid regolith will vary a lot depending on the size of the body. So a small asteroid like Bennu or Ryugu, recently visited by spacecraft, those had very, very coarse. There's essentially no regolith on the surface of those small, half-kilometer sized asteroids. It was just boulders, very little regolith. A large asteroid like Vesta, which is one of the largest asteroids, will have regolith that is finer, maybe closer in texture to the lunar regolith. And there's been some interesting observations of small asteroids, like the asteroid Eros has these dust ponds. So it does have small concentrated areas of very dusty regolith interspersed with a very kind of boulder-rich surface. Mm-hmm. So it's really dependent on the size of the body and whether the gravity environment of that asteroid can maintain small particles or whether they just get lofted into escape velocity from impacts.
This is Sean. Hi.
Hey.
First of all, very nice talk. I just have a quick question about the agglutinate that you described. And the question is, you show those pictures with agglutinate down to millimeter size. Does those extend to smaller particle sizes? Thank you.
Yeah. So in the lunar regolith, there are a pretty big range of agglutinate sizes. Some are significantly smaller than a millimeter. I think millimeter scale is probably the biggest of the agglutinates. And our simulated agglutinates are probably on that scale, on the biggest end. So we're figuring out how to make them smaller while still maintaining the right properties, the right morphology. yeah, they can be quite fine because they're getting on the lunar surface, they're getting broken up all the time by more impacts.
I see. Thank you.
Yeah, sure.
And does the electrostate charging play any role in the regolith transport, or sticking around?
Yeah. So that's not a topic I know a lot about. At our university, Dr. Addie Dove and Dr. Josh Caldwell both study that in detail. Yeah, but electrostatic transport is an important regolith process. And we're trying to better understand how well our simulants simulate the actual lunar regolith. It's a little bit hard. It can be a little bit hard you have to have the right conditions to study that. You have to have a vacuum, and you have to sometimes being in 1G, having an atmosphere, adsorbed water on your particles, stuff like that, that will all affect those properties. So it's important to have, if you're studying that, you have to have the right environment to do that in. So I don't personally work on that, but yeah, I know my colleague Addie Dove is one of the foremost experts on that.
Mm-hmm. Very good. My final question is that that the moon has a very, very tenuous atmosphere, and helium, hydrogen, oxygen, but the most interesting thing is about the xenon and neon. And recently, people are talking about those rare gas like xenon might interact with the regolith. Could those processes be simulated in the lab? I mean, those are absorption and desorption, of regolith as a function of time, temperature.
Yeah, I know exactly what you're talking about. I guess I don't want to say I'm not familiar enough with how you would do that in the lab. I do know what you're talking about, and I imagine somebody's working on that, but yeah, I don't. That's too far out of my realm of minerals and and dirt. I don't know. It's a good question.
Seems that there's one question because of the LADI and this kind of measurements. Even the Apollo measurement, people look at it again, and they look at the detail, and this kind of the gas and regolith interaction is essential in understanding this.
Yeah, no, absolutely. That's an important question.
Okay, great. Anyone have questions? If not, of course, I have other questions, but I think I don't want to drag on for too long. And thank you, Landsman. Such a very nice, wonderful talk. And to begin this, I hope that your talk will attract more your colleagues to come to give talks, and because they're very interesting, important things, working in your lab. And I thank you so very much. Yeah.
Thank you. Yeah, thank you so much. Thank you so much for inviting me. If anybody has more questions, you're welcome to email me. So thank you. Well, we will soon
ask you to come back to give another talk.
Wonderful. Thank you.
Okay, thank you so much.